Okay. Okay. Let's talk briefly about the time of flight mass spectrometer. I prepared this maybe some times ago. Okay. Number one is when we are dealing with time of flight. Time of flight is not the name of a spectrometer. It's just a technique. Okay, it's just a technique that is adopted to um adopted to studying certain properties of elements. Okay, that's what it's from. So time of the flight in the spectrometer use the principle of time of flight. Okay, now what's the principle of time of flight? The principle is that electromagnetic waves, there are some groups of waves that we call the electromagnetic waves. They are Gaxulia, okay, Gaxu, Limra, okay. This is radio wave, microwave, infrared, light waves, ultraviolet, X-rays, alpha rays, and gamma rays. Okay, all of them collectively are called um, electromagnetic waves. Okay, now so the principle is that electromagnetic waves travels through a vacuum. Um, it doesn't travel through material medium. It doesn't require material medium for its propagation. So it can travel through a vacuum. So that property is exploited by some scientists to study properties of certain elements. Number one, it has been found that in a vacuum, if electron is traveling, it hits an object, it travels back at the same speed of light back to the source. So if it takes 2 seconds to get to the end here, it's going to take equally 2 seconds to get to the back. So we can use the idea of the time to estimate certain properties of the element here or compound or any substance at the end here. So that property is exploited by scientists, okay, to study certain compounds. So that's where the word time of flight comes from. So how does time of flight mass spectrum works? There are a number of chamber. Okay, the first chamber is the sample chamber, where you're gonna put the sample. Now the sample, it has to be very careful. If you were asked to describe the working principle of the time of flight mass spectrum, which is expected that you know. Number one, you must be able to mention that the first step is to injection step. Okay, first step is injection. Now injection is the addition of sample into the sample chamber. Okay, now the sample you're adding must be in liquid phase or gaseous phase. It's very important. Sample cannot be solid, so it has to be in liquid phase or gaseous phase so that electrons can be easily knocked off. Okay, now the next one is the if it were solid, it will be turned into powdery and or liquid form or gas. Okay, so the next one is if it were even liquid. Okay, let me highlight that very well. If the sample you're putting there is gas, there is no need to do anything. Okay, if the sample you're putting there is liquid, the liquid will be evaporated. Okay, they will be turned to gas. So basically what should move from the gas chamber, from the sample chamber, is actually gas. Okay, what should move from here to this place will always be a gas. So no matter what you put in the sample chamber, somehow you have to turn it into a gas. Okay, but it's easy when you put liquid to turn it to gas then solid. That's why it is very important that the sample you're adding should be either liquid or gas. So now that we understand that the sample should be in those two forms, the next thing is after the sample is placed into the sample chamber, the next one is going to be ionized. Ionization, remember in chemistry, is the loss or gain of electron. Ionization is the process of losing or gaining electron. But in this case, we are ionizing the sample by losing electron. What I mean by that is that as the particles are evaporated here, there will be release of electron. This chamber uh, contains some elements, filament that can radiate electron. Remember I mentioned electromagnetic radiation. There are radiations like gaxulim. I gave you the example. Now the one we use here is electron. Is a very fast moving electron. So what happens is that it will collide with the particles, the gaseous particles of the sample. And let's say this one particle electron will come and knock it out. So one electron here will be removed um by the fast moving electron, but you don't need all the details. All that you know is that um it will be ionized. Ionization means the removal of electron by another electron. Okay, the removal of electron by another electron. So because it has become ion, so it will become either positively charged or negatively charged. It's very important to understand that it's become either positively charged or negatively. But I already told you in this case that we are knocking out electron, so it will be positively charged. Okay, we are knocking out electron, so that means it's losing electron. It's going to become positively charged. Now immediately it leaves the sample chamber, it will enter into this chamber. Now you could already see that this region are negatively charged. They are negatively charged. If you recall from the basic principle of physics and chemistry, we'll make to understand that unlike charges tend to attract each other. Unlike charges will tend to attract each other. Like charges will tend to repel each other because everything coming out from the sample chamber is positively charged. Okay, they will be equally attracted towards the towards the negative chamber, towards the negative electrode or pole. Okay, I want to take this off. They will be equally attracted towards this region. So that attraction is what we call acceleration. Okay, so the ions are attracted or accelerated towards the negative charges. Okay, because the ions are positive, so they'll be accelerated towards the positive charges, towards the negative charges. Now this pushes them towards the drift chamber. This region is the drift chamber. Okay, that's the drift chamber. Now what happens in the drift chamber is that the electrons, because they have moved away from the negative charge, once they enter into the drift chamber, they slow down. Okay, but not like they slow down. um their movement is controlled by certain particle, which I'm going to talk about. Now immediately they enter into drift chamber. Now the movement is no longer on a linear state, it is now a curved movement. Okay, they bend. Now I think I was mentioning to you that this region has something we call magnetic field. The drift chamber is contained in magnetic field. So the detector typically is not really here, it's actually somewhere by the side. Okay, it's not really at the center, but it's easy to put it at the center so that you can understand the basic working principle. But typically it's actually somewhere by the side. So what happens is that immediately the charged particles from the sample has escaped the negative charge and enters into the drift chamber. What would happen is that they will start moving across the magnetic field. So because when particles move across the magnetic field, okay, when particles that are charged, ions, when they move across the magnetic field, they move in a curved path. They don't move straight. Okay, you should understand that principle now. They do not move on a straight line, so they curve, they bend. Okay, now as it's moving up and bending across the curve, it's going to go to hit the detector. Now once it hits the detector, it will be discovered, it will be detected by the detector, and that detector will produce a spectrum. Okay, an image like a graph showing the estimate of what has hit it. Okay, now there are two things that I have wanted to take note of. That now I said the magnetic field makes them move in a curved path. um until it until they hit the detector at different velocity is very important. Now I told you now, once they are moving the same speed, okay, you have to understand it. The speed at which they move inside this chamber is the same. They move at uniform speed inside this chamber. But immediately they enters into the drift chamber, they move at different speed. Okay, so it's very important you understand that. Here they move at the same speed, here they move at different speed. Now, why did they move at different speed in the same chamber? Because they are not accelerated. They were accelerated in this chamber, remember? But here they were not accelerated by anything. So they move at their own regular speed, different speed. But the movement is not a straight movement, it's a curved movement controlled by the two magnetic field, by the magnetic field in the drift chamber. So immediately they bend across that, they go straight um to hit the detector. Now this is where it's very important to understand. Now because they move at different speed, they are going to arrive at the detector at different time, and they are going to move at different velocities. Okay, those are the two things that we use to measure both the abundance and the estimate of the relative atomic mass. Okay, the time taken the time taken to get to the detector by different ions will be used to measure their mass. Okay, now the amount of current, because each time an electron hits the detector, current is released. Now I want to explain that. Remember I told you that when electrons move and they hit a particles on the compound, they kind of knock out electron. Okay, when electron move and hit another particle, another atom, it's going to knock out an electron from it. So it's similar to the way that ions, now remember these are ions, they are charged particles. So once they hit the detector, there will be a flow of electric current. It's very important. Once they hit the detector and the detector is about to find out the kind of atom that has hit it, there will be a flow of electric current. It's like a signal, okay? It's like a signal, a unique signal by every atom. Their own signal is different, okay? So let's look at it as a signal from the ion on the detector. That current is not what is to be used to measure its abundance. So that means the higher the current, the higher the abundance. So if the current is more, it will have a larger abundance. If the current released is small, then it will have a lower abundance. So those are the key things. So this is the summary of it, okay? And when you're mentioning your the mass spectrometer, you must mention that the interior of the machine is a vacuum. It's very important. The interior of a machine is the vacuum. Why did they say it's a vacuum? A vacuum is technically a region that contains no air, okay? That contains no medium. Like there is no air there, there is no water, okay? It's just an empty space. That's a vacuum. So now, why do we have to mention that the interior of the machine is a vacuum? The reason we have to mention this is because the particles that are moving inside the vacuum are extremely sensitive particles. For example, ion, ion that is formed from the sample chamber. If there is air there, air might contain nitrogen, for example, and probably the ion that is coming is calcium. Now I have a problem because if there is calcium and nitrogen, my detector will detect nitrogen and to also detect calcium. So I will not be able to tell which one is my element. So for purity, number one, the reason at the inside is vacuum is to get a pure result, to get an accurate result. That's number one. Number two, to also ensure the movement of electrons easily, because electrons or electromagnetic waves only move through vacuum. Okay, they move through vacuum. That means they move through empty space. They don't need a material medium for their propagation. So very good example of it is when you talk about the sunlight reaching the earth. Okay, it moves through the vacuum. It doesn't have a connector between the sun and the earth. It just radiates. Okay, an example of vacuum. So this is a typical working principle of the time of flight mass spectrometer. Okay, now let's now estimate how to do calculation of this. What do we calculate? We actually calculate. Okay, let me see that. Oh, I thought I snapped that. It's not here.